So we mentioned a long time back that x rotations, y rotations, and z rotations are actually entangled at an infinitesimal level. In other words, even very, very tiny rotations about these axes are somehow intertwined. So let's finish this lesson by seeing precisely how using Blender. So first let's state the relation. So let's let rho x, rho y, and rho z denote infinitesimal rotations about the x, y, and z axes. It turns out that rho z is then equal to rho x times rho y times rho negative x times rho negative y, where, as usual, we're reading these operations from right to left. So really we're performing an infinitesimal negative y rotation, then an infinitesimal negative x rotation, then an infinitesimal positive y rotation, and finally an infinitesimal positive x rotation. So in the following animation, we're going to approximate rho x and rho y by 15-degree rotations about the x and y axes. So not really infinitesimally small, just small. But the z rotation is not going to be exact, but it's still going to be very apparent. All right, so this relation between tiny rotations that we just witnessed, it'd be very difficult to observe purely through movement, because a 15-degree or an even smaller degree rotation with Bala is hard to perform consistently and see that this z actually pops out. So that's a little hard to see with movement, but with the algebra of quaternions and with Blender, it becomes very apparent. So that's quite cool. In fact, a more general relationship also holds. For any vector v, let's let rho v denote the infinitesimal rotation about the axis spanned by v. I'm being a little bit imprecise. I mean, I'm not going to precisely define infinitesimal rotations. I just mean a very tiny rotation with respect to that axis. So rho v denotes an infinitesimal rotation about the axis spanned by v. Given two vectors v and w, with cross product vw, remember that given a vector v and a vector w in space, the cross product is a vector that's perpendicular to both of them. Given these three vectors, we have the following relationship. Rho v cross w, that's the infinitesimal rotation in the direction of v cross w, that's equal to rho negative w times rho negative v times rho w times rho v. This expression that I just wrote is known as the Lie bracket of rho v and rho w, and it's sometimes denoted bracket rho v comma rho w. So another way of writing this relation is that rho v cross w is equal to bracket of rho v and rho w. And as a special case, we have that rho z is equal to the bracket of rho x and rho y. So we mentioned earlier that SO3 is more than just a space. It's something called a Lie group, which is both a group and a differentiable manifold. So it has both a geometric structure and an algebraic structure. And this means that we can study, because it's differentiable, we can actually study its tangent space at any point. In a differentiable manifold, something like this, at a point x, you can look at its tangent space. And in particular, since it's a group, it has an identity element, and we can look at its tangent space at the identity. The tangent space at the identity is known as the Lie algebra of a Lie group. In general, the Lie algebra contains the infinitesimal seeds of movement in all possible directions in the Lie group. But since our Lie group is SO3, its Lie algebra consists of infinitesimal rotations. And the Lie bracket operation shows exactly how these infinitesimal rotations are entangled with each other. via that relationship. So a Lie algebra is not all that interesting topologically. It's just flat, like any tangent space. And yet miraculously, this is the words of John Stilwell in his book Naive Lie Theory, the miracle of Lie theory is that the curved structure of a Lie group is almost completely captured by this flat structure of its Lie algebra. Somehow the Lie bracket and which is this product of the Lie algebra and this entanglement of infinitesimal rotations somehow completely determines most of the structure of the Lie group of orientation space. So Lie theory is the theory of Lie groups and Lie algebras and how they're connected. And it provides a natural framework for everything that we've studied so far. On the other hand, even if your interests lie outside of pure math, quaternions and spatial rotations are very, very useful. They tend to show up in all kinds of applications involving movement in space, which we've already discussed, like anything involving computer graphics or robotics. So I hope that whenever you encounter quaternions or spatial rotations in the future, you'll remember your explorations with Bala in all his many avatars.